Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 42, we will cover runoff estimation. This is the first part. The different concepts that we will cover will be on the requirement for runoff estimation, return period selection, time of concentration, rational method runoff coefficient determination, and peak flow estimation using rational formula, and finally, we will solve a problem. So, in the previous lecture, we have learnt about the basics of how to design sewers, or the size of the sewers, or the slope of the sewers. Now, we have done it when we have estimating it for the sewage flow, then there is no issues. We can do that based on the sewage flow for a particular area. But when we also design sewers for storm water, we first need to estimate the runoff that is generated for a particular catchment. So, but that generation of runoff, how much actually reaches the point of inlet, that itself is needs to be first computed. Then, based on that amount of runoff that reaches the inlet, plus the then for that we have to design the sewer. So, in case it is a separate system, then we have to design a sewer for only the storm water flow. But if it is a combined system, then both sewage flow and then the storm water flow taken together, and then we have to design the sewer. So, first, before we design storm water sewers, we have to first understand how we estimate runoff for a particular area. So, runoff estimation basically involves catchment routing. The term catchment routing is related to whenever a rainfall happens, not all, some part of the rainfall, we call it effective rainfall, is actually forms a stream and flows within the catchment and reaches the inlet. So, catchment routing transforms effective rainfall into stream flow within a catchment. So, that means whenever rainfall falls on a catchment, some part of the rainfall moves on the catchment, moves over the catchment as runoff, and then reaches the inlet point. So, this is called catchment routing. Now, as you can understand, we have already discussed this concept of time of concentration, but again I will elaborate that on it further. That is time required for water to travel from the furthest point in the total catchment to the point of consideration, or in this particular case inlet. But whenever we are considering the surrounding area from the inlet, we can say that the maximum time required for the water to start from the farthest end of that area and reach the inlet. But this is direct water that comes to the inlet. But if this inlet is within a particular pipeline, that means the water in the water that comes from the upper sections of the pipeline, those are also coming from certain other catchments. So, we also need to consider that as well. So, that means the water that comes to a particular point reaches not only from the surrounding land, but also from much far away, which comes via the pipeline where that water has entered into some point in that pipeline in some other inlet. So, it is not only the surrounding area, but also all upstream areas that needs to be considered. So, time required for water to travel from the furthest point, that involves for the entire catchment and for all upstream areas, even and not only the adjacent area to this particular inlet. So, intensity, we also know that intensity of rainfall varies as per the time of concentration. So, intensity of rainfall varies as per the time of duration of rainfall, and intensity of rainfall has to be taken for this time of concentration. That means the time required for water to reach from the furthest point to the inlet, that time is called the time of concentration, and that for that particular duration we have to determine intensity. So, that means that is the chance when the highest possible rainfall can happen. We have also discussed about something called the partial area effect, where maximum flow or peak discharge may occur when only part of the upstream catchment is contributing. So, we are saying that in the first we said that time required for water to travel from the farthest point to the total catchment. Why we say that? Because that means the entire catchment's water will be coming to that point of consideration. But that is not the case in case of partial area effect. In partial area effect, it says that maximum discharge may occur when only part of the upstream catchment is contributing. Why? Because time in that case would be lower and the intensity of rainfall during that time could be higher, as we know that smaller durations result in higher intensity. So, smaller area, higher intensity together gives discharge. This could be more than larger area, lower intensity. So, that is the partial area effect. So, there are different methods to determine runoff. Again, we have discussed all this earlier as well. That is the rational method, time area method, unit hydrograph method, and the rainfall runoff process simulation. So, rational method we have also learned earlier as well. So, in rational method, this is the most simplest method that we can utilize, and we have already done calculations using rational method earlier, but there are some differences on how we use it to compute runoff for a particular inlet, or the amount of water that goes into a storm, into a particular storm. So, the process is a little bit different. Let us look at those different steps. The first step is first demarcate the catchment area. This is the first step. Select return period as per area or infrastructure under consideration. So, we need to consider what would be the return period. That means, at what frequency of interval we will we will consider this particular intensity of rainfall to happen. So, from that we have already discussed how to determine that. Obtain IDF curves for this area or prepare IDF curve for this area as per historical rainfall data. Determine the time of concentration. Determine rainfall intensity as per the time of concentration from IDF curve. Determine runoff coefficient and estimate peak flow using rational formula. So, you can understand that there are several assumptions that has to be considered when we use rational method to determine runoff or the amount of water that goes into a particular inlet. Now, why it is so? First of all, rainfall intensity as per time of concentration we will take from the IDF curve, which we select as based on the return period. So, this actually will help us to identify the right intensity. So, it is not a rainfall intensity of a particular event, but this is the possibility of of rainfall which can happen during a particular considering a particular return period. So, we will consider the maximum intensity that is possible for that duration. So, that is which will give us the maximum possible runoff that will be formed, and then runoff coefficient C, that means again for the entire catchment area we can have single C value, or we can have different kind of land uses in the catchment area. So, we can have a composite C value as well, and then using both these two we can determine the total amount of runoff. But as you can understand that the runoff that we are considering, it is like the intensity during the entire duration for this period is more or less same. If it is for a small period, no issues, but if the period is like 6 hours or 8 hours, intensity varies over the entire time. So, no effect for that is considered, and so on. So, we will discuss those issues as well. So, first of all, how do I determine the return period, right? So, return period is basically the frequency or return period of a storm event, and it could be defined as the average recurrence interval between events equal to or exceeding a specific magnitude. So, that means, if I choose a intensity of 90 millimeter per hour and the return period I can say like 5 years, that means this 90 millimeter per hour happens for that particular duration of rainfall happens for a period of every 5 years it is repeated. So, that is the basic concept behind the idea of return period. Now, this return period selection depends on the importance of the drainage area, socio-economic conditions and constraints such as funding and availability of space. Now, how are these related? So, that means if I consider a return period of 100 years, that means I am giving much more protection to my infrastructure. That means within a 100-year period, whatever rainfall value, maximum rainfall was there, I have for that particular duration, I am choosing that particular value. Now, this makes it, that means our design would be safe even for very for 100-year period also, it is probably the design is adequate. But that means that means that of course the cost of this kind of infrastructure would be higher, because if you have to design something for higher levels of rainfall and all, that means you have to consider higher amount of water, and accordingly everything has to be, probably if it involves flooding, so things has to be raised or other flood protection measures has to be created. So, this will be cost money. So, socio-economic conditions will determine also the return period, and other constraints such as immediate funding availability, availability of space for creating those kind of infrastructure, all this determines what should be the return period. Now, usually for central business districts and commercial areas, for class 1 cities, we take a return period of 5 years, whereas for other smaller cities, we can take a return period of 2 years. Similarly, for industrial areas, we take it for 5 years and 2 years for smaller cities, urban residential 5 years, and airports and other critical infrastructure almost 100 years, and maybe for smaller cities 50 years. Critical infrastructure also include railway stations, power stations, which should not get inundated in case of any kind of heavy rainfall. And class 1 cities are cities having population more than 1 lakh, and other cities are less than 1 lakh. So, that is the thing that is the classification for as per Indian standards. In exceptional cases, higher return period is justified for particular infrastructure or particular kind of situation. We can justify higher return periods, but it has to be for a particular infrastructure which actually requires that kind of protection. So, limitations in adoption of design or return period can be overcome by provision of rainwater harvesting structures and stormwater retention structures to accommodate the excess runoff. Sometimes we cannot design something for this excess return period, like because we do not have funds, or maybe because of certain other issues, we cannot choose that kind of a return period, or we cannot over design our infrastructure. So, that could be compensated by creating other kinds of infrastructure which would help in detention or retention of some amount of this runoff, or by creating this rainwater harvesting structures. So, this is one way to compensate for lower return periods. And there is also a growing consensus that this we have discussed earlier as well, that in some cases as per CPH EEO, this is the standards that is provided in India, 1 or 2 year return period or 12 to 20 millimeter per hour is inadequate in the current context, because considering climate change and sudden extreme weather patterns or sudden rainfall events, we are seeing that we are getting much more rainfall compared to this, and this is leading to a lot of flooding in many of our cities. So, this has to be really looked into once more. So, now coming to time of concentration. So, this is basically used in determining the maximum runoff in a sewer section. So, we need to determine the sewer section based on whatever is the maximum runoff that it would carry during in the course of its lifetime, right, in the course of its design period. So, when the entire catchment contributes to the flow for this particular sewer section or this particular inlet point, the time required for the same is the time of concentration for this sewer section. So, when the entire catchment contributes to the flow, so we are saying this, in this case partial area effect is not considered. So, if I considered partial area effect, maybe the entire catchment even though does not contribute, it may have also the maximum flow, but the idea is we need to determine the maximum runoff in the sewer section. So, in most cases the entire catchment will contribute. The other thing is the intensity of rainfall which lasts for a period of time of concentration is considered contributing to the flow of stormwater in the sewer. So, intensity is uniform throughout the storm event. So, that is also one of our assumptions. So, that means intensity of rainfall for that duration, and that duration is same as the time of concentration. So, time of concentration for a particular inlet or a particular section is measured using two components. One is the inlet time and the other is the time of travel in the drainage system or in the sewer system. So, that means the water that comes to a particular point could come direct. Suppose we have a pipeline, I think we have an illustration for this later on. So, inlet time or surface or overland flow time is the time required for the rain in falling on the most remote point of the tributary or catchment area to flow across the ground surface along drains or gutters to inlet of sewers. So, that means it flows in natural channels or maybe some design channels, maybe at the gutter of the streets, and it ultimately reaches the inlet of a sewer. So, this is the time required for water to travel from the that remotest point that we talked about. That is when the entire catchment has to be covered. So, we consider the remotest point, and that time takes it to reach the sewer. So, this is the first part, inlet time. The second time is the time of travel, is the time required by stormwater in traveling from the uppermost inlet up to the point of concentration. So, that means this is the time taken by the water once it has entered the inlet, then it travels along the sewer line to the point of which we are considering now, or to the section which we are considering now. Each section has to be designed separately. So, time of concentration for each section will vary. Okay? So, this time of concentration is both inlet time, that is the overland flow time of water, plus the time it takes from for the water to travel from the first inlet to the point to the inlet which we are considering now. So, this is determined based on length of drain divided by velocity of water in the drain. And as we know, the velocity of water could be determined using Manning's equation, or it could be used in Hazen-Williams as well. So, it depends on in what context we are using this equation. So, if it is this pipe network is full, that means in that case sometimes we go for Hazen-Williams, but if it is partially filled, then we will go for Manning's. So, we can use this formula V equal to 1 by n r to the power 2/3 into s to the power half. R is hydraulic radius, s is slope, friction slope. So, this could be utilized for determining the velocity of water in the drain, and based on the length of that particular drain we can determine the time of flow. So, as you can see, this is the entire catchment that is being covered by this particular sewer network. And like over here, point of if for this particular point, the point of concentration, we will only consider the time taken by water to reach from this particular farthest point to come inside the inlet. So, this is the first inlet. So, only inlet time is considered, there is no time of travel in the drainage system. But when I decide the size of this particular sewer, then that means it depends on we need to determine what amount of water flows for this particular section. Whatever water comes into this inlet, that is considered while designing this section. But when I consider designing this section, then the water that enters into this inlet is from the surrounding area, plus the water that comes from this point to this, where it travels over ground to this and then travels along the pipeline and comes to this point. So, in this case, both the farthest point for this particular inlet is again this one. So, here water comes from using inlet time and then time of travel along the sewer network. So, that is how we determine the point of concentration, and also water comes from this point and so on. So, we have to determine that. So, that is how we will determine the total time of concentration for each of these points of consideration, based on which we will determine the quantum of the maximum runoff that would be generated for this particular case. So, if we have the time of concentration, we have the design period, and then we need to determine the runoff. So, before that, just that inlet time, how do I determine inlet time? As you can understand, this is the time required by water to flow over ground and reach this particular point. So, that means we assume in most cases it is not flowing through some artificial channels, or even so it is particularly related with the slope of this particular land, right. So, that will determine the speed at which the water will reach this, or the time in which the water will reach this first inlet. So, shape, characteristics and topography of the drainage basin, this actually influences the inlet time and usually varies from 5 to 30 minutes, and in developed areas where there is lot of in urban areas and all, it could even be something like just 3 minutes. So, this is that inlet time more or less that we actually see, and there are different empirical formulas that has been developed by different researchers. So, Corps of Engineers USA formula, this is the one which is most commonly used. This is the formula that is used. T0 is equal to 0.994 into 1.1 minus C into L to the power 0.5 divided by S, or slope, S to the power 0.333. S is surface slope in percentage, L is length of surface flow, C is the rational runoff coefficient because it is flowing over ground. So, that means some amount of water is infiltrated. So, that is why C value is taken, and then the rest are constants. So, this is one formula that you can use to determine the overland flow, or you can use this formula as well, where T0 equal to 0.885 into L cube divided by H. H is the total fall of level from critical point to the mouth of drain. So, that is the difference in height, and L cube is the distance. So, which gives you the slope, distance by slope, and all to the power 0.385. So, L is T0 is the time of surface flow in hours. So, this is what any one of these two formula could be used. This one is surface flow in minutes and this one is hours, and based on this you can calculate the inlet time, whereas the flow time within the sewer network could be determined using Manning's formula or any other formula. For each storm sewer section, for each inlet, drainage area should be indicated, demarcated and measured. So, this is the first requirement. That means, for each inlet we should know exactly what is the drainage area, and tributary boundaries depend on topography, land use, nature of development and shape of drainage basin. So, based on that we can determine the catchment of that particular point. So, for each point in the network there is a catchment area, and that is how we determine based on topography, land use, nature of development and so on. So, we will show this in subsequent lecture. We will do a detailed lecture on how to determine catchments. So, the rational method of runoff coefficient. So, in this method the runoff entering the sewer depends on the imperviousness of the catchment, which includes both the land use and the runoff coefficient for that particular catchment. If detailed data is not available on the land use as well as the runoff coefficients for that particular catchment, then we can assume that if it is a commercial and industrial area, we can take around 70 to 90% of imperviousness. If it is a residential area, then we can take these figures. If it is parks and undeveloped area, we can take around 10 to 20. So, these are the assumptions if you do not have the data for land use, exact data for land use or the runoff coefficients for those land uses. So, plus we need to have idea about the shape of the drainage area and the duration of the storm. So, these are the basic information that we require. So, two other things, that is longer periods of light rain saturates the soil. That means, if the rainfall is happening for a long period, then automatically the soil gets saturated, and this leads to higher runoff coefficient, because no further water can go down. So, that there is a maximum possible amount of water that can infiltrate. After that, the runoff coefficient will increase. Heavy intermittent rain, that means it is heavy rain, but it sometimes happens, then it is not there. In this case, lower runoff coefficient since less saturation. So, these are two things which happen, but in this particular method we actually cannot consider this variation too much. So, saturation, this is one. The other the point that you will see is saturation near point of concentration influence the runoff more than areas further away. Why? Because most of the runoff from different areas comes to this point, and if this area is saturated, then obviously there would not be percolation. So, the quantity of water is higher and you are not able to, infiltration is not happening over there. So, that actually influences the amount of runoff that is generated. And a larger area can be subdivided into zones of concentration, and the runoff coefficient can be decreased for distant zone. So, this is one strategy people follow, but anyway, so it is not that important for urban catchments. The catchments are pretty small. We may not be able to do this kind of estimates. There is no requirement as such. In case of multiple surface type, a composite or weighted runoff coefficient is determined. So, we have done this earlier as well when we have done our runoff calculations earlier. So, that is area multiplied by this weighted average imperviousness for that particular area. So, I1, I2, In are the runoff coefficients of respective sub areas multiplied with the area divided by total area gives us the weighted average imperviousness for that entire area. So, we use this weighted value based on the different land uses that are there. So, this is a table that is provided by CPHEO, where different shapes of catchment are considered, like it is a rectangle, length is equal to 4 times width, or it could be something like a sector shape, like we can divide into different sectors. And here you can see that for different duration of rainfall, like 10 minutes, 20 minutes, 30 minutes, 45 minutes and so on, the imperviousness actually the factor changes. So, the more duration the rainfall, the imperviousness value, this factor actually increases, right, because less amount of water would be infiltrating. Similarly, 60% imperviousness, these are the values, this is fully impervious, and 40% imperviousness, it is even lesser value. And but still if we go, the duration becomes higher, then this value actually increases, and then if it is pervious, then these are the values. So, if again the duration is higher, the value is increasing. So, impervious surfaces has got higher coefficient, which means more runoff is generated. Similarly, higher duration, more runoff is generated. Similarly, you can get these figures for other rectangular shape catchments as well. So, now we come down to the final calculation, where we have Q equal to 10 into CIA, where C is coefficient of runoff, I is intensity of rainfall, millimeter per hour, A is drainage area in hectares 10 to the power 4, and 10 is just the factor, which because we are doing it meter cube per hour and not meter cube per second, we end up with 10 CIA. So, this is the most popular formula to determine this stormwater runoff, and this is applicable to 90% of urban catchments, because most urban catchments are pretty small. So, that is why we can apply this formula, but this method can be applied only with certain assumptions that I was discussing at the beginning as well. So, the total discharge is equal to coefficient into intensity of rainfall. This is as per the time of concentration or the duration of rainfall, which is same as the time of concentration, and A is the area of that catchment, and I is weighted C is the weighted value of the coefficient. So, what are the assumptions that we do to for this kind of using the rational formula? This method can be used for determining peak flows only for small catchments. Now, usually it is said that around 200 acres of area is fine, that is 0.81 square kilometers, but if it is more than that, then we have to look into other formulas. But CPHEO has said that up to 8 to 10 square kilometers we can even go for use this kind of formula, and the time of concentration for the drainage area is less than the duration of peak rainfall intensity. So, that is one assumption that we are doing, that is time of concentration is less than the duration of peak rainfall intensity. The peak flow occurs when the entire catchment is contributing to the flow. So, this is another assumption, partial effect is not considered. Runoff is directly proportional to the rainfall intensity, which is uniform throughout the storm. The frequency of occurrence of peak discharge is same as the frequency of rainfall producing it. Rainfall is distributed uniformly over the surface drainage area. Minimum duration of computation of rainfall intensity is 10 minutes. We cannot go with time of concentration less than 10 minutes. So, at least that much amount of rainfall has to be considered. The coefficient of runoff is same for all storms for all recurrence probabilities. So, that means we do not consider the moisture conditions of the catchment and so on. So, these are some of the limitations of applications of this model. We assume same intensity all throughout the storm event. We do not consider differences in the area. So, these are so many limitations, but still in urban catchments this is fine, and as you can see 90% of urban catchments could be covered by using this particular formula. Means we will get proper discharge estimates using this formula. So, let us solve a problem. Design a section of a combined circular sewer from the following data. We have area to be served is 140 hectares, population of locality is 40,000, maximum permissible velocity of flow is 3.4 meter per second inside this particular pipeline. Time of entry is 6 minutes. We have not given you any, there is no need to compute that. Already we are giving you the value of time of entry as 6 minutes, that is the time taken by the rainfall from the furthest point to reach this particular inlet is 6 minutes, and time of flow is 22 minutes within the particular sewer section, and rate of water supply is 250 liters per day per capita, and impermeability factor is 0.45. So, first what we will do is we have to design the combined circular sewer. So, that means we have to understand the amount of water that is generated due to rainfall as well as from the sewage that is generated from this particular community. So, because it is a combined sewer. So, first let us determine the sewage that is generated. So, quantity of water supply is 40,000 into 250 divided by 24 into 60 into 60, that is for minutes and seconds, and this is hours. So, this gives us around 115.74 liters per second. So, this is the quantity of water supply or the flow rate, and assuming the maximum discharge as 1.45 times the average of this value, this is 1.5 into 115.74, which comes to around 173.61 liters per second or 0.173 cubic meter per second. So, this is the discharge that is generated from sewage. So, you can always take 80% and then multiply by 1.8 and so on. Overall, we have taken given a factor of 1.5. So, this you are free to use those kind of assumptions. So, storm water, now let us determine what is the storm water that is generated. So, time of concentration is 6, inlet time is 6, 22 time is the flow time in the sewer. So, that gives us around 28 minutes. So, intensity of rainfall has to be determined for 28 minutes duration, right. But we do not have a IDF curve provided with this particular problem. So, instead of using picking up the right value from the IDF curve, we compute the intensity of rainfall. Again, the design period is also not given. So, the return period is also not given. So, we use the empirical formula where I equal to 25.4 into A by T plus B, where T is duration of storm in minutes, A is 30 and B is 10 when duration of storm is 5 to 20 minutes, and A is 40 and 20 when duration of storm is more than 20 minutes. So, in this case we have 28 minutes. So, we choose A is 40 and B is 20, 40 and B is 20, and 25.4 into 40, this is the value that for A, and T is 28. So, we get around 21.17 millimeter per hour as the intensity of rainfall. So, now we have to determine that. So, 10 for total rational formula gives us 10 into CIA. So, that is 10 into 0.45 into 21.17 into 140, which is 13,337.1 meter cube per hour. So, that comes to around 3.7 meter cube per second of flow that is generated because of storm water. So, now because it is a combined flow, we have to add both the storm flow as well as the sewage flow. So, when I add 0.173 and 3.7, we get 3.873 meter cube per second as the total combined flow for this particular sewer section, and this is the peak flow. So, now Q is equal to A into V. So, A is equal to Q divided by V, which comes to around 1.139 meter square. So, therefore, diameter of the sewer is d equal to root a into 4 divided by pi, which comes to around 1.204 meter. So, therefore, to provide a circular sphere of diameter 1.2 meters. So, this is the way we solve this particular problem. So, we have to first determine the sewage flow, we have to determine the flow due to storm water, the runoff, and then we have to add those two up and then determine the sewer section that is required for this. So, to conclude, for small urban catchments, the rational method is adequate for determining runoff volume. However, the time of concentration and the return period has to be carefully chosen. For determining time of concentration, it is important to determine both inlet time and time of travel in sewer. So, these are the references you can use. Thank you.